do a unitary transform on the vector. This is called unitary transform. You change the vector into a new direction. Then what it says is that the inner product, the length of the vector doesn't change. Okay, if I were to find the length of this vector in a new space by finding its conjugate transpose dot v, is just equal to v conjugate transpose dot u conjugate transpose dot u dot v. And by the definition of the unitary operator, this piece is I, and then this is the v. Okay, this is one good property. Another nice property is that inner products do not change. Okay, if I were to perform a unitary transform, and then if I have another vector u that I perform the same unitary transform with, u prime, u prime. If I were to find the inner product between u prime and v prime, okay, we can substitute in, it's the same as before. Okay, it's very easy to show that this inner product does not change. So inner product and length do not change in unitary transform. Another very important property of quantum mechanics is the property of Hermitian operators. And we can draw a lot of the properties that we have learned from linear algebra, except for a few. Okay, so in linear algebra, a Hermitian matrix is one where this is satisfied. If you take the transpose of a matrix and conjugate the element, it becomes itself. This is what we learned from linear algebra. And this concept is harder to define in a Hilbert space. And in linear algebra, we can define that element by element. We reduce the definition of a Hermitian operator to this definition. But actually, it should follow from an inner product definition that if a matrix A, a vector A times a matrix M, dot with a vector B, and if you were to take its conjugate transpose, okay, this is a scalar number. The conjugate transpose of a scalar number is itself. Okay, and then we apply the rule of matrix algebra that we learned in linear algebra. Okay, this becomes this times that times that. Okay, from the rule of linear algebra. So this thing can be used to define what a Hermitian transpose is. The Hermitian transpose, or the conjugate transpose of a matrix system, is a matrix M dagger that satisfies this inner product, both on the left and the right hand side. And what we have done actually is to use this fact. I hope you know this fact, that if you have a matrix A times a matrix B times a matrix C, if you take its transpose, it's just equal to that. You can prove this very easily from linear algebra. Okay, that this can be generalized to conjugate transpose, the dagger, equals dagger times B dagger times A dagger. And I have just used this property to rewrite this. These are non-square matrices. Okay, you can think of them as non-square matrices. This applies to any non-square matrices when you multiply them. Because of this, we can actually use Hilbert space inner product to define what the conjugate transpose of a Hilbert space operator should be. Okay, so it's very hard to write the conjugate transpose or the Hermitian transpose of the M hat operator using this kind of notation because we do not know what the matrix elements are. Okay. However, we can use inner product definition and say that if I were to take the conjugate transpose of this number, I should get, it's the same as this actually. Okay. Conjugation is the same as conjugate transpose since these are scalar numbers. And then applying this rule that I have just learned or shown above, that this is G conjugate transpose, which will come up it converts from a cat vector to a bra vector. And then this will be conjugate transpose thing. So I can use this to define what a conjugate transpose of a Hilbert space operator should be. It is an operator that when you plug in here, that it should satisfy this inner product. So we have generalized this kind of definition into a more abstract definition. It can be used in Hilbert space. Okay. And then there are things like orthonormality, orthogonal, orthonormality of eigenvectors. That I think we proved before in chapter 1 or something. So I won't prove this. Okay, you can prove that these Hermitian operators would also have that kind of property. But let's take a very simple example. That we have learned in this course that P hat is a momentum operator. Okay, and when we look at this P hat operator in its raw form, we do not know whether it's a Hermitian operator, right? It's not obvious to you because you're going to see things like that. But you know that it's an operator. In order to prove that this is a Hermitian operator, you have to perform tests like this and show that this is itself. Then it will become, and then it can be proven that it's a Hermitian operator. So how can we use this to prove that this is a Hermitian operator? So we take inner product. We take this with the vector f and take its conjugate transpose, which by definition of what we had over there should be P hat f. Okay, by definition of what a Hermitian transpose is, this is what P hat should be, or P hat dagger should be. It should be something that satisfies this equation. So in order to evaluate this inner product, you can perform the integration on the left-hand side. Okay, if you perform it without a dagger, you should have a star here, you should have a minus here. But if you take this star inside, you only have a star on that term. Okay, this is the left-hand side. Left-hand side equals that. You can make integration from minus infinity to infinity. Left-hand side equals that. Let's see if you can cast it into something that looks like the right-hand side. Right-hand side has this P hat operating on F, but now this P hat is operating on G. So we want to make this operate on F. What rule and what trick can we apply so that this operates on F? What trick can we apply so that we come up with a form that have this operate? Integration by parts, right? Is something that we often learn in school. Okay, so we have to do integration by parts. And if we do integration by parts, then first you integrate this term first, and then evaluate the two limits, and assuming that these functions g and f are functions that vanish at infinity. So the first term that comes out of integration by parts goes to 0, and then what you have left is the second term. And then now this operator operates on that now. There is a minus sign introduced by integration by parts. So after performing one integration by parts, I get that. I suppose that all of you know how to do integration by parts, right? So if you look at this, this is exactly in the form of the right-hand side. And I must identify this to be my P hat Hermitian transpose or conjugate transpose. Okay, and then I find that my P hat is equal to P, exactly what I started out with. So this must be a Hermitian operator because this conjugate transpose is itself. Okay, so that is a way that you can prove if a operator is Hermitian. You can do that for 2D and 3D too. In the lecture notes, we have one done for 2 and 3 dimensions. Okay, but the proof is very similar. You have to learn how to do integration by parts in 2D or 3D. Okay, I think I wouldn't go into that and let you do that. You can study the more complicated 2-dimensional and 3-dimensional forms. Okay, and do integration by parts. Would it be of interest if I go through the 2D or 3D case? I guess not. You can read up on yourself. Read up by yourself. Okay, the 2D and the 3D case. This is the 1D case. Okay, let's move on to something else that is perhaps more interesting. The expectation value of an operator, which I say I will define. Okay, so I'd like to talk about commutation of operators, and then after that talk about expectation value, and that should be enough for today, I think. And I skip a number of things in the lecture notes. You can read them up by yourself if you're interested. Okay. So in general, like matrix algebra, this is not true. This is not true in operator algebra. Okay. And the commutator A comma B is defined to be A comma B or AB minus BA. Okay, this is called the commutator. And if A and B are commuting matrices, like diagonal matrices or some class of matrices, then if they commute, if this is equal to 0, this implies that AB equals BA. Very few matrix or very few operators do that. And a very simple example of matrix operators that do that is the diagonal operator. But there are some other operators that commute with each other as well. Okay, in general, they don't commute. Okay, and you can show that in general, A comma B is equal to IC. If A is Hermitian, B is Hermitian, their commutator produce a matrix C that is Hermitian if you add an I in front of it. Okay, you can actually show this quite easily. If I expand this out, it's A comma AB minus BA. And if I take the Hermitian conjugate transpose of both sides, I IC hat conjugate transpose is equal to, if I take this conjugate transpose and knowing that these are all Hermitian matrices, okay, this would become B hat, A hat conjugate transpose minus A hat, B hat. Okay, if I use this rule. Okay, but these are Hermitian matrices, so they are just B A minus A B. So this is just minus the commutator. Okay, so when you have this kind of thing, okay, so this must be equal to just
because the operators are Hermitian.
So this must be IC, okay, because it's minus the operator, this must be IC, which means that C conjugate transpose must be itself. Yes?
Are we assuming that the operators are Hermitian?
Yeah, A and B are Hermitian operators. Okay, if A and B are Hermitian operators, when they commute with each other, they produce a third matrix C hat, which is also Hermitian. if we put an I in front, and this is the proof. Okay, this is the proof for it. Okay. And also, if two operators commute with each other, they're either diagonal operators or identity operators, or they are operators that share the same eigenfunction. Okay, they are operators that share the same eigenfunctions. You can prove that quite easily. Okay, so if A comma B is equal to 0, which means that they're commuting, then it's quite easy to show that B hat A hat size of n, where size of n is say the eigenfunction of one of them. Okay, this must be also equal to A hat B hat size of n, because they're commuting operators. But because size of n is the eigenfunction of B, so I can replace this with its eigenvalue, Bm size of n. Okay, I can replace this with its eigenvalue, and then I can exchange the order A hat size of n. Okay, so what this says is that if psi n is an eigenfunction of B hat, okay, A hat psi n is also an eigenfunction of B hat. That's what this says. Okay. If psi n is an eigenfunction of B hat, A psi n is also an eigenfunction of B hat, which means that this must be written as another eigenfunction, must be the same as some of the eigenfunctions. Okay. So this must be something that is proportional to size of n. That is what it says. Okay. So A hat size of n must be equal to a constant, or maybe a constant size of n. Okay. So they share the same eigenfunctions. Otherwise, this would not be true. This must be linearly proportional to size of n. Okay, can you see this proof? That if they commute, this is true. If this is true, and if psi n is an eigenvalue of B, this is true. And then you can put this out front, and it will compare this with that. And this is an eigenfunction of B as well. Okay, if this is an eigenfunction of B, then A times psi n must be an eigenfunction itself. Okay, because eigenfunctions of B belongs to this set of functions. Okay, and then the eigenfunctions with the same eigenvalue. So it must be something that is proportional to the same eigenfunction. Because of that, then this must be true. That size of n is also an eigenfunction of A hat. Okay. Are there any questions so far? Let me try to explain this again, okay? I think this one to this one to this one is quite logical. Okay? So this one times this one must say that this must be an eigenvalue of B with the same eigenvalue too. So this must be true. Okay, this must be true. A times psi n must be a constant times psi n. Okay? So this means psi n is also an eigenvalue, eigenfunction of A. So this must be true. Psi n is an eigenfunction of A, because if it's not, when you multiply it by A, it shouldn't be just a constant times the eigenfunction. Okay? So this thing, C sub n, must be the eigenvalue of this matrix A. Okay, is this clear? Or is this not clear? It's clear, right? So I see a lot of nodding here, so this must be true. Okay? So let's So what is the physical meaning of the expectation value of an operator? We have learned in quantum mechanics many operators, like a Hamiltonian operator is written like something like this, plus something like that. Okay, this could be a position operator, and usually we just replace it with a scalar. And that we call P hat plus G hat. We can think of this as a diagonal operator if you want to. Okay? And these operators that we have physical meaning. The first one we say has something to do with the kinetic energy. The second one we say has something to do with the potential energy. So operators, they have a physical meaning, are also called observables. Something that you can think about in the real physical world that perhaps you can also measure, like the potential energy of the particle plus the kinetic energy of the particle. It can also be things like momentum, like we just learned before. And then if you write down the momentum operator, it is something like this in 3D, and there should be an I over here. And it was something like this in 1D. Okay, and momentum operator can be converted to something like this. We just proved that this is summation. You can also prove that this is summation if you know how to do integration by parts in 3 dimensions. So proof is very similar to that. And these are all called observables because they have an association with a physical quantity that we know exists in the real world, okay, at least in the classical world. So in order to connect quantum mechanics with the real world, we find expectation value of this operator in terms of the state the quantum system is in. As we said before, the quantum system is defined by a state of the wave function, or defined by the wave function. The wave function can be 1 dimension or 3 dimension, depending on whether you're solving a 1D or 3D problem. And this describes the state of the electron. The electron is in this state when it is described by this wave function. And then the energy state that we have studied before. Okay, these are called the energy state. These are the eigenvalues of the Hamiltonian. And these are also called stationary state, as we have alluded to in chapter 1 of the chapter. Because they are time independent, they're stationary in the time domain. If you take their magnitude square and look at the time variation, they do not change with time. That's why they're called stationary states. Okay? So in order to relate these operators to the real world, we have to multiply by the state function and then get the values and then further multiply by another state function, and that's called taking the expectation value of the operator. So what is the meaning of taking the expectation value of an operator? So if we have an operator A hat, it can be one of those operators that we described. The expectation value of this operator is just equal to that. This F defines the state in which the electron is in, or the quantum system is in. Okay? The state could be a stationary energy state, or it could be a linear superposition of the energy state. It doesn't matter. It is one of those states. Okay? It is a state used to describe the electron. Okay? So we can expand this state of the electron or wave function in terms of, say, some orthonormal eigenstate, which could be the energy state. Okay, we can expand the arbitrary state of the electron in such a manner, and size of n could be one of these energy states. Okay? So what does the expectation value mean then? If you look at the expectation value, then the expectation value of A hat is equal to, if I substitute this into the above, then I will have something that looks like that. Size of n, A hat, size of n, Fn conjugate Fn. Okay, because when I take the transpose of this, I have to conjugate this thing over here, and then take the transpose. When I take the conjugate transpose of this and plug that in there, I have to conjugate this term. So I get Fn star over there. Okay? So this is the expectation value, but it has a special meaning. If you pick size of m to be the eigenstate of the operator A hat, if you pick this in such a way that this is true, if you pick the eigenfunctions that you expand the operator, the function f in terms of to be an eigenfunction of the operator A hat, then this thing simplifies, the expectation value simplifies to something that if you plug it in there, you will get, this is replaced with an eigenvalue of am, you get psi n, psi m, and then you get fn, fn star, you will have sum over n and m, but then this becomes orthonormal, it just becomes delta nm. We define these eigenfunctions to be orthonormal with respect to each other, so one of the summations would drop out, and then n would become m after the summation. Okay, so finally you are left with only one summation, and that being equal to that. Okay, but we have the probabilistic interpretation of quantum mechanics before. Okay, that in the probabilistic interpretation of quantum mechanics, this has to be normalized to 1. Any state functions that is used to define a quantum system has to be normalized to 1. Because this thing, if you take its magnitude square, okay, this is just the, in one dimension it will be just something like that. Okay, in 3 dimensions it will be something more complicated. Okay, so this is the magnitude square of the function which we have defined to be the probability density function. Okay, so this is like a probability density function in probability theory. Okay, and it has to be normalized to 1. So if we have this normalization, it's quite easy to show that f bar f, okay, f inner product f is equal to 2 of these multiplied together, and m psi n fn star. Okay, you can do this very easily by just plain substitution, and this becomes delta mn, and this summation just becomes fn squared. And this also has to be equal to 1. Okay? So when you do a change of basis like this, even the coefficients themselves have to sum up to 1 because of this normalization. So the coefficient squared summing up to 1 means that this can also be interpreted as a kind of a probability distribution for discrete things. Okay, so this is the probability distribution. So what does this mean? This means that if I have a state vector f expanded in terms of this orthonormal function, the magnitude squared of this coefficient is a probability of finding the state in this eigenstate. Okay, this is the probabilistic interpretation of quantum mechanics. Because all these numbers add up to 1, so each of them must have the meaning of a probability of being in that state. So the coefficient square indicates the probability of finding the quantum state in this eigenstate. That is the physical meaning of this expansion. Okay? And if you look at this now, the expectation value of the operator A hat in terms of its eigenfunctions, okay, is just the eigenvalue of the operator A, this is the eigenvalue of the operator A, multiplied by this thing, and this should be thought of as a probability distribution, okay? The probability of finding the quantum system in this eigenstate size of n. And so this is like AN PM, and it's equal to 1 to infinity, say if you have infinite eigenmodes. And this is the probability weighted average. So this is kind of a weighted average of the eigenvalues of the system in terms of a probability distribution. So you can think of the expectation value of an operator the physical meaning of it being that if you have an operator, the physical meaning of that is that find the eigenfunctions and the eigenvalues of this operator, okay? Expand the quantum state in terms of those eigenfunctions, and then the expectation value of this operator would be just the expectation value of the eigenvalues themselves, which can be written in many probability courses, like just A bar. Okay, the expectation value of the eigenvalues themselves. So is this clear? What the expectation value of an operator is? Okay. So if we prepare a pure quantum state that this thing only has one eigenfunction representing it, which means that it is in a pure eigenstate of the operator. Okay, it's quite clear that then if you were to take the expectation value of the A hat operator in this state, it would be psi n A hat. Psi n would be just the eigenvalue of the state. Okay. And if two operators commute, if A comma B is equal to 0, which means that the eigenstate that I have that belongs to the first operator is also the eigenstate of the second operator. So if I were to take the eigenstate with respect to the same state, the eigenstate, the expectation value of the operator with respect to the same eigenstate, I would just have the eigenvalue. Okay. What this means is that if two operators commute, you can find eigenstates that define the eigenvalues exactly, and they don't get mixed up with each other. Operator B will have the exact value of B sub n. Operator A will have the exact value of A sub n. That is the meaning when two operators commute. Okay. What happens if they do not commute? What does that mean? If two operators do not commute, I cannot make claims like this anymore. Okay. If A comma B is not equal to 0, if they do not commute, then if I have the eigenfunctions of A, they are not necessarily the eigenfunctions of B anymore. Okay. So I might be able to expand the eigenfunctions of A in terms of the eigenfunctions of B in this manner. Okay, this might be true, or this can be true. This belongs to B. Okay, this belongs to B hat, this belongs to A hat. And because they are not commuting, they don't share the same eigenfunction. So I have to do that expansion. Whereas before that, because they commute, they share the same set of eigenfunctions. And this gives rise to a different interpretation. It says that if I prepare a quantum state, then there's a pure quantum state that is in the eigenstate of the operator A hat, I can get the expectation value of the first operators to be exactly A sub n. But then when I try to find the expectation value of B, okay, because of this expansion, the expectation value of B hat is equal to, I have to substitute in this right there now and get something, okay, this will be psi n, B hat psi n. If I substitute this in, I'll get a double summation. Okay, if I substitute in and get a double summation, I get AI conjugate AJ psi I B hat psi j. With these are phi, okay, these are phi, these are psi. The phi's are the eigenfunctions of B. And I can simplify them. AI, AJ, and then this might be something like B sub j psi I psi j, because they define the psi j to be the eigenfunctions of B, the phi j. So I can replace that with an eigenvalue Bj, and this is delta Ij. So this finally becomes just one summation Bi. So you can see that something prepared in a pure quantum state for operator A is spread over the sum of different eigenstates with different eigenvalues. So if something is very pure for the operator A hat, you have only one pure eigenstate, and then if you go to the operator B hat, it has to be summed over a whole bunch of eigenvalues. That's what it means. Okay, that's what it means over here. A pure state becomes